This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. Not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic, and I'm happy to stick with the status quo here, because at the end of the 2 videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants, but in these 2 introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between, called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16? Well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network as an information processing mechanism comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now, the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now, in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents, or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number, but for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like -10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer, and each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases. 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposefully tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weighted sum of the activations in the first layer, according to these weights, corresponds to one of the terms in the matrix vector product of everything we have on the left here. By the way, so much of machine learning just comes down to having a good grasp of linear algebra, so for any of you who want a nice visual understanding for matrices and what matrix vector multiplication means, take a look at the series I did on linear algebra, especially chapter 3. Back to our expression, instead of talking about adding the bias to each one of these values independently, we represent it by organizing all those biases into a vector, and adding the entire vector to the previous matrix vector product. Then, as a final step, I'll wrap a sigmoid around the outside here. And what that's supposed to represent is that you're going to apply the sigmoid function to each specific component of the resulting vector inside. So, once you write down this weight matrix and these vectors as their own symbols, you can communicate the full transition of activations from one layer to the next in an extremely tight and neat little expression. And this makes the relevant code both a lot simpler and a lot faster, since many libraries optimize the heck out of matrix multiplication. Remember how earlier I said these neurons are simply things that hold numbers? Well, of course, the specific numbers that they hold depends on the image you feed in. So it's actually more accurate to think of each neuron as a function, one that takes in the outputs of all the neurons in the previous layer and spits out a number between 0 and 1. Really, the entire network is just a function, one that takes in 784 numbers as an input and spits out 10 numbers as an output. It's an absurdly complicated function, one that involves 13,000 parameters in the forms of these weights and biases that pick up on certain patterns, and which involves iterating many matrix vector products and the sigmoid squishification function. But it's just a function nonetheless. And in a way, it's kind of reassuring that it looks complicated. I mean, if it were any simpler, what hope would we have that it could take on the challenge of recognizing digits? And how does it take on that challenge? How does this network learn the appropriate weights and biases just by looking at data? Well, that's what I'll show in the next video. And I'll also dig a little more into what this particular network we're seeing is really doing.
이전 동영상에서는 뉴럴 네트워크와 딥러닝이 무엇이고 어떻게 동작하는지에 대해서 알아보았습니다. 이번 시간에는 아티피셜 뉴럴 네트워크에 대해서 간단히 강의하도록 하겠습니다. 왼쪽 테이블에는 attribute x1, x2, x3와 클래스 y의 값들이 표시되어 있습니다. 오른쪽에는 Artificial Neural Network이 블랙박스로 표시되어 있고 attribute x1, x2, x3가 인풋으로 되어 있으며 y가 아웃풋으로 되어 있습니다. 우리의 목적은 왼쪽 테이블을 만족시키는 블랙박스 안에 Artificial Neural Network를 구현하는 것입니다. 본 사례의 Artificial Neural Network는 인풋 노드가 3개가 있고 아웃풋 노드가 1개 있습니다. 그리고 인풋 노드와 아웃풋 노드를 연결하는 엣지가 3개 있습니다. 이것을 식으로 구현하면 y는 sin 0.3x1 더하기 0.3x2 더하기 0.3x3 마이너스 0.4가 됩니다. 이때 각각의 엣지와 연관된 0.3 값을 weight라고 하고 아웃풋 노드와 연결된 0.4 값을 threshold 혹은 bias라고 합니다. 주어진 식에 x값들을 대입해보면 클래스 y가 성공적으로 분류되는 것을 볼 수 있습니다. 오른쪽 그림을 보면 weight를 W123으로 표시하고 threshold를 T로 표시한 것을 볼 수 있습니다. 이러한 모델을 perceptron 모델이라고 하는데 인공신경망의 가장 초기 모델에 해당이 됩니다. 이를 식으로 표현하면 y는 sin 시그마 i는 1부터 d까지 wi xi-t가 됩니다. 맨 아래 식은 i가 0일 때 w0 x0가 -t인 것으로 설정해서 식을 간편하게 표현한 것입니다. 뉴럴 네트워크의 일반 구조입니다. input X는 input 레이어에 연결이 되어 있고 input 레이어는 히든 레이어를 거쳐서 output 레이어에 연결되며 output 레이어는 클래스 Y를 예측하게 됩니다. 오른쪽에는 녹색으로 표시되어 있는 i번째 뉴런에 대해서 좀 더 자세히 보여주고 있습니다. 뉴런 I에 연결된 인풋이 I123라고 하면 weight 123가 이에 곱해져서 sum si를 계산하게 됩니다. 그 값에 activation function g를 적용해서 gsi를 계산하고 threshold t를 적용하면 output oi가 계산됩니다. 뉴럴 네트워크를 훈련시킨다는 것은 이러한 뉴런의 weight 값 w들을 학습시킨다는 의미입니다. 뉴럴 네트워크 토폴로지에는 여러가지 종류가 있습니다. 퍼셉트론과 같은 싱글 레이어 네트워크도 있고 멀티 레이어 네트워크도 있습니다. feed forward, 순방향도 있고 recurrent, 시퀀스 데이터를 처리하기 위한 순환 네트워크도 있습니다. 각 뉴런의 노드는 인풋과 아웃풋을 매핑하는 액티베이션 펑션 F를 가지고 있는데 오른쪽에 보면 linear function, sigmoid function, tangent hyperbolic function, sine function 등이 있습니다. 퍼셉트론은 가장 간단한 뉴럴 네트워크로 싱글 레이어 네트워크입니다. 단 하나의 인풋과 아웃풋 노드만을 갖고 있습니다. 액티베이션 펑션 F는 sine 함수인데 모델을 적용하는 것은 아래 예제에 나와 있는 것처럼 매우 간단합니다. 퍼셉트론의 학습 규칙입니다. 처음에는 W0부터 WD까지 모든 웨이트를 초기화합니다. 다음 단계에서는 트레이닝 데이터 XI, YI에 대해서 웨이트 값을 조정하는 것을 계속해서 반복합니다. 여기서 웨이트 값 W를 조정해 나가는 것이 바로 학습이고 이에 대해서 좀 더 살펴보겠습니다. 웨이트를 업데이트하는 공식입니다. WK 플러스 1은 K 플러스 1번째 업데이트된 W입니다. WK는 K번째 업데이트된 W입니다. 람다는 러닝 레이트로서 람다 값이 크면은 W가 빠르게 변하고 람다가 작으면 W가 작게 변합니다. YI는 i번째 트레이닝 데이터의 클래스이고 XI는 i번째 트레이닝 데이터의 애트리뷰트입니다. F는 액티베이션 펑션으로 K번째 W와 XI를 바탕으로 아웃풋 클래스를 예측합니다. 트레이닝 데이터 YI에서 이 F값을 뺀 것을 에러 E라고 합니다. 만약 트레이닝 데이터 클래스 Y가 F와 같으면 이 값은 0이 돼서 업데이트가 필요하지 않습니다. 만약 Y가 F보다 크면 에러 E가 0보다 커서 웨이트를 증가시킵니다. 반면에 만약 Y가 F보다 작으면 E가 0보다 작고 이때는 웨이트를 감소시킵니다. 다음은 퍼셉트론 러닝을 통해서 웨이트 값 W0123가 어떻게 학습되는지를 보도록 하겠습니다. 아래 왼쪽 테이블을 보게 되면 attribute x123가 있고 클래스 y가 있습니다. 이 값들을 위에 두 식에 단계별로 대입합니다. 이때 러닝 레이트인 람다 값은 0.1로 하였습니다. 두 번째 테이블에 보면 이 단계별 계산을 통해서 W0123가 계산된 것을 볼 수 있습니다. 초기 값은 0000이었지만 8단계의 학습을 통해서 -0.2, 0, 0.2, 0.2가 되었습니다. 이 값들은 오른쪽 테이블에 있는 에포크 1, 시대 1의 웨이트의 초기 값들이 됩니다. 이번에는 에포크 1의 초기 값으로 트레이닝을 해서 에포크 2의 초기 값을 얻을 수 있습니다. 이런 식으로 에포크를 반복할 수 있는데 이상적인 것은 웨이트 값들이 어떤 값들로 실험해 가면서 에러는 0에 가까워지는 것입니다.